As we come into our second session, our speaker is going to be Brian Gandy. He is the Vice President of Research and Operations at Valoya, and he has the title of his talk up here. So, Brian. We can give him a round of applause.
All right, well, thank you, everybody. This is an honor. I asked to speak the first time I heard about this event, and it's been 3 now, so thank you for having me. And I was a brief student in the program, but I've been out selling lights instead. But I still think about this constantly, and it's a really fun topic. Plants and light, I can't stop thinking about it, so hopefully I put more information in last night. Hopefully this tracks. The first time I gave this speech was in Morocco. Second time was in UC Davis, which I was in completely over my skis there. But I know at least half or more of you in the room, so I appreciate you guys coming, most of you. And and my family's here too, so this is an honor. Thank you guys. So right now, if you don't know what PPFD is, we'll get into that. But as we design lighting systems for cultivation, we are using basically a combination of terminology that is an amalgamation of visual perception and agronomics. And PPFD, I'll get into the definition, and I'm going to point out a few other things that I've seen along the way. Basically, working in the private sector is really exciting because we see things that are, I would say, impossible. So then I get to go back and reverse engineer and see how people did it. So my old trope is cannabis is a gateway drug to horticulture. We're gonna add controlled environmental agriculture and now physics to that. And like I said, the impossible observations I've seen, people who are growers that you just can't say no to, and then they do things that I can't tell them no. So I've been working with cannabis for a long time, before it was legal and after. I was a hemp farmer for a couple years, and this was my first LED grow back in 2014. We were using ducted hoods and cobs growing. That was Durban poison. That was definitely bootleg days, I think. But we've come a long way, and actually I think this is a picture from y'all's facility down in Anna with the photo bleaching, which was the first time I've ever seen this at lower light levels, and I've been working on it ever since then, and I think I might have that one figured out, but that's not what this presentation's about. But this is just generally accepted in horticulture or in cannabis. We know what causes it, or we know what parameters cause it, but we don't know what actually causes it. Dr. Bruce Bugbee at Utah State is a thought leader and has been forever on horticultural lighting. And he's defined the parameters that if you have more than 70% red in your spectrum at certain intensities, you're gonna see this. But I was able to see it at much lower light levels and not under LED. So that will be what I'm talking about next year. And these are just a couple of my other earlier trials. I was working with autoflowers in different spectrum and morphology response. That was my favorite pot I ever grew, was a pre-98 Bubba Kush under LED that we had engineered. And that was 2016. I think that was the last time I actually grew for myself indoors. But now I get to work with real scientists. This was a chemovar expression trial with our partners out in Oregon. So it's just a real honor to get to work with such professionals and scientists out in the field to learn from them and then feedback that information and knowledge, or at least try to process it. So I'm going to put out a lot of ideas that I need help actually solving. So hopefully there's some budding scientists in the room. And one of the main things that makes cannabis extremely unique is the structure of the plant itself. So when we're growing mostly in controlled environmental agriculture, we're looking at lettuce, mums, ornamental plants, very much a two-dimensional plane of canopy. And cannabis, when we're growing it indoors or in a greenhouse, is a three-dimensional plant. I mean, we're trying to get flowers from top to bottom. We want marketable product from top to bottom. And that provides unique challenges because when we're supplementing with artificial lighting, we're looking at what traditionally we correlate in literature and science and studies on a two-dimensional plane, but we've actually got a three-dimensional subject now, which brings unique challenges and opportunities. So, PPFD on Canopy, and then daily light integral. These are the two terms I'm going to define because this is where we've run into a crux on terminology. So on the right, we have our spectrum running 100 micromoles on clones, but with a unique spectrum, it's enough to grow very healthy plants at a good rate. And then here is just another top lit. You can see how high the fixtures are from the canopy. And this is a facility in West Virginia that we work with that does a very good job as well. But when we're designing and doing lighting layouts, anybody who's ever bought lights or been annoyed by a lighting salesman, we will send out these lighting designs that are done in either Dialux or AGI 32. And we use this software, which is a derivative of like landscape lighting or architectural lighting, visual perception lighting. So we do map out the best uniformity that we can. However, there's still some flaws. You can see that there's uniformity issues. There's drop-offs on the side. We can address this in a lot of ways. I've seen some new science coming out. A lot of people trying to address it with controls or fixtures. We've done unique layouts where we'll actually put more fixtures on the outside of the room, tuck the lights right up to the edge of the room. But this is what goes as the industry standard. And 1,000 micromoles on canopy used to be the industry standard. And then I have this grower up in Michigan who is definitely a bootlegger, but we basically couldn't tell him no. He's like, I'm going to put 1,800 micromoles down on canopy. And we said, no, you're not. And then this is what happened. This is Kush Mints, and anybody who knows the industry probably knows who this grower is. It's his cut, and you can see, I mean, he's got 4 feet of full canopy of harvestable and sellable flower. And this is nearly double the amount of light level that we would prescribe historically. And he was getting over 130 grams per square foot indoors. And I said, well, now I have the next couple of years to figure this one out. So what is on canopy? I mean, all of the newer genetics, like the GMOs for all you growers out there, are long, stalky, and leggy. So we have plants that'll grow straight up to the light. And there's one scientist up in University of Guelph who actually did a better job of defining the term in her publication. And we've talked, and she agrees that there is a fundamental gap in the understanding of how we do lighting design. Because this canopy, again, this grower's got 3 feet deep of flower, of sellable flower. So the plant doesn't necessarily care. There's not a clear top off. I mean, this is a 3-dimensional space. So the definition of on canopy is in the mix and not quite defined yet. And then from the agronomic side, we have daily light integral, which is in a cornfield, PPFD from a light meter, but it's times the math, it's the integral of the total amount of light that you get in the season. You're going to determine when your corn is harvested by the total amount of light that it gets over time. These are the USDA maps, so if you're designing a greenhouse or you're looking at producing certain field crops, you would go to these to say, I'm going to be able to grow corn here. On average, I'm going to be able to pull my crop down in this many days because it's going to get this much total light energy over time. But this is an agronomic term that has been used. And while the math adds up with a light meter in a cornfield, there's a disparity between artificial lighting and the sunlight. So in the literature and my PhD friends, I knew I was onto something when I made one of my favorite and smartest PhD friends slap the table and told me that I cannot challenge the fundamental laws of physics. The inverse square law is the inverse square law. It's a law. You can't change the law. And it's like, I'm not changing the law. We're just using the wrong terminology. It is absolutely true, but it's based on human perception. And like for our photography friends, it's key for designing systems and taking good photos, shooting good film. However, it's from a point source. So this is a candle. If we set it in the middle of the room and had a light meter and moved away from it, the numbers would be a logarithmic decay based on the distance from that point source. And the term PPFD is photosynthetic photon flux density. I always get nervous saying that one in person out loud. But technically, density is the amount of energy or mass in a three-dimensional space. What we have here is actually an aerial density. This is a two-dimensional plane that's being managed and monitored and designed to. So we are applying a two-dimensional measurement and specification to a three-dimensional system. That's problem number one. So right now, this is 26.1 watts per square foot. This is 700 micromoles going down to under 100, going from 1 to 10 feet. That follows the rule pretty well. It's not a perfect representation of the inverse square law, but it does track and it does correlate to what the law says. But the second line is 20 watts per square foot. And the rate of decay is completely different, and it doesn't taper off. And it's not flat, but it's much closer to flat. So how is that possible? Well, if we hang one light in the middle of a room or the middle of a space, you get closer to that logarithmic rate of decay. But we are designing systems, we're designing arrays. I mean, the basic ceiling of a grow room or a greenhouse is a very large two-dimensional space. So this is not apples to apples right out the gate. And I noticed this for the first time when double linders first came to the market. I went into my first Gavita room and I saw these 7-foot tall plants, and I climbed up on a ladder with a light meter, and I got up to the top and it was only at 750 micromoles. I was like, well, that's weird. Like, it should be 1,000 here, but the lights were still 5 feet above the top of the canopy. And I did some measurements going down a distance, and I was like, well, that doesn't follow the rule. This was 2015, 2016, whenever Gavitas were starting to get commercially deployed. So that's when the hamster wheel started turning, and I lost a lot of sleep. So again, just looking at different wattage densities in a system, because we're not dealing with a point source, we're dealing with systems engineering at this point. You can see the 26.1 grams per watt. Watts per square foot does have the curve, but we can pretty much plateau that line by putting more light into a room and into a system by raising the lights. You know, it's non-traditional thinking. Everybody thinks you need to put a racking fixture 6 inches away from the canopy to get 1,200 micromoles to get your yield. The reality is, if we put enough light and enough energy into the room and into the system, the yield is based on the total rate of inputs, not on the level of a two-dimensional plane. So this was an earlier rendition. I did the other data set last night, but this is what, it shows this line plateaus at 1,000 micromoles. Obviously, you're going to run into the canopy interference and shading, and everybody talks about penetration, which is I've got a fun YouTube video out there if anybody wants to watch it. When I was discussing this topic 2 years ago or 3 years ago, board during the pandemic. But this means that we're flooding the space with light. And the physics of light are very strange. But this is not a point source of light. These fixtures are 6 or 7 feet from the canopy. This is a 200 light room with 100 and some varieties in it. And he's hitting his yield numbers and his quality numbers here. Even though if you put the light meter at the top of the canopy, it may be 800 or 900 micromoles, he's still getting his, whatever his metric is. Everybody wants around 2.5 to 3 pounds of light. We're getting some guys getting up to 4 pounds per 600 to 800 watts now. So new heights are being reached on yield potential, but I am specifying top lights at a minimum of 5 feet away from the canopy and not trying to force the light on the top of the plant, because what happens, and you see it with high pressure sodium, you get a really dense flower at the top, and then you get a really loose, larvae flower at the bottom. And one thing I noticed, again, when I first started running trials with LEDs, is that the uniformity of the quality of the flower from the top to the bottom of the plant is much more consistent than it's ever been with HPS. There's other reasons for that. Going back to that photo bleaching, again, that'll be next year's topic. because of the heat that comes from a high pressure sodium lamp. But, having lights up out of the way, and the Dutch do this unintentionally, the greenhouse methodology, they always want to put fixtures 8 feet from the plants. And I always question that, but it makes sense. And I don't know if they've taken credit for it now, so I will. But, being able to pull your numbers and keep your hardware out of your hair is key. So this is the difference. I mean, when we have a point source, even if it's in a system or an array in a room, we're going to look at 2,000 micromoles right under the light. It's going to decay down to this rate. If you go out in a cornfield with a tall ladder or in a greenhouse with a light meter, you're going to see 2,000 micromoles. So obviously the sun's a lot further away. The math adds up. There's still some decay on that total amount of energy, but the distance that we're looking at is negligible. There's no difference. And I was talking to a professor who was working on corn at Cornell, and he's like, how do I grow 15-foot tall corn plants indoors? I was like, you need to put your lights 15 feet above it and put a lot more energy in. It's going to be wholly inefficient, but for crop science, this is what you need to do. And he's like, you're absolutely right. No one here believes me. So I got at least one other convert. And in a greenhouse, you get a hybrid of these things where it gets more complicated, but this is where radiometrics and agronomics fall apart. So as far as the terminology and systems engineering, we're looking at this from an optimization standpoint. We're looking at efficiency, we're looking at reducing energy and getting the most output from your inputs. So I took this screenshot from a video. There's a lot going on right now in the science of the physics of light. If you guys want to enjoy some cannabis and sit and watch hours of good footage, Niles Berglund has a bunch of very high resolution mathematic demonstrations of how light works through different materials. And I actually, there's the thinking that, and it's known that light has particle properties and wave properties, but the wave properties are what are most applicable and we're finding it to be most true. And when you get waves, you get things that act like a physical thing, like water. So basically this is light moving through a drop of water, and you can see it's condensing, and then you'll get interference and it'll bounce back through and get re-angled. And another thing that we're doing when we're running LED rooms is we're running the humidity much higher than we would in HPS rooms. So there's another physical interface that we haven't really looked at yet, is the physical interface between water and light and water suspended in the atmosphere. So you get this diffusion, diffraction, and refraction of light so that it almost acts like a gas. Obviously there's the direct incidence, but we need to look at light on a much smaller level, itty bitty level, and this is what they're doing with modeling. And in plants, there's also some unique characteristics with chlorophyll and transmission through the leaves. But our understanding of light is going to improve because of our understanding of light in plants. And another case in point, this is using a penny, but you could also have a leaf. Light will actually move around and reconvene behind something that it runs into. And I thought this comic was kind of funny. Can your stream of particles do that? So wave theory, light theory, and physics is, again, where I'm starting to spend a lot more of my time. So this is an image. It looks like the Northern Lights. Anybody know what this is? Light pollution from a greenhouse light. This is across the Michigan River. Got it, Zach. So this is a mix of LED and HPS light diffusing out of the top of greenhouses. And the reason we can see it from a distance is because the water in the air, that cloud, is actually redirecting the light to come to our eyes. So this makes the point that humidity and moisture in the air actually change the light physics and how it moves around in a room or in the system in the environment. So that's another thing that in the literature, it's not really been considered much. So while we're designing systems, especially for vertical farming, everybody's looking to optimize efficiency. If you're growing lettuce under a sole source lighting in a warehouse, everybody's bean counting. Every input counts. I mean, it costs money and fuel to run these things. So we are still designing on a two-dimensional plane when we actually have a three-dimensional consideration of canopy, depth of canopy, crop interference, shading, diffraction, refraction, and then also some unique activity, the way chlorophyll actually opens up and lets more light through once it's saturated. And this is an old image from one of my heroes, Dr. Bruce Bugbee, and this was from the 80s, where he was talking about, and it was fun actually, in Morocco I had a physicist call me out and say these numbers were BS, and that's actually true. Did you have a question?
No, 5 minutes.
5 minutes, okay, cool. But the point remains, it takes X number of photons to create X number of carbohydrates to create X number of grams of biomass. What angle those come from, how they're delivered, how they're received, how they're captured and converted is what we really need to be looking at. Yeah, 1988, he was way ahead of the game, and he still is. But we need to rethink the way that we design light systems, controlled environmental agriculture, and efficiencies as a result. So this is another tie-in because light and sound are very closely related, actually. And I stood on a stage in 2017 in front of a room of horticultural lighting professionals and gave this concept, and I got crickets. But there's starting to be more and more validity to this. Plants perceive light like we perceive sound. So we look at major and minor tonalities. You know, there's slight shifts in sound that make us perceive our mood changes when we hear a minor note versus a major note, or you add a 12th or 13th, you get jazzy, and like plants react to light like humans react to music. And again, one late night on YouTube, this thing came up. I was listening to the math of music theory, and these numbers came up, and it's 440, 660, and 733. And in the lighting world, that's blue, that's red, and that's far red. In the music world, that's Baba Black Sheep in A. Hertz and nanometers aren't the same, but I thought that the tie-in on the numbers and the overlap was pretty profound. And anyway, the story goes on. So I do want to thank all the people that have inspired me to get to this point. Bruce Bugbee, I mentioned, Dr. Van Ertzel, who actually just recently passed away. Actually, on the day that I got to speak at the conference he was supposed to be speaking at. Erica Matos, Ryan Hunt, and a good friend and now colleague, Christopher Sloper. So that's it. Any questions? Right on time.